Wait, why are we even studying electric dipoles? And what even is an electric dipole? Let me answer the second question first. An electric dipole is a pair of two equal but opposite charges separated by a distance. So this is not a dipole because the charges are different, but this is a dipole. Now, why are we studying electric dipoles? First, because it's in our course outline. But why did they feel the need to put it in our course outline? To stress us? Well, because electric dipoles are special. They behave differently from any other random pair of charges, and dipoles are also very present in chemical molecules in our world. So how do they behave differently? If I want to find the electric field due to any other two random charges, let's say +5 and -3 coulomb, at a very far away distance r, as we go far away, the two random charges will begin to appear as a single charge, and we can calculate the electric field by simply finding the net charge and using it in the Coulomb's formula. Kq over r square will be equal to Kq net over r square. Q is the net charge, which is +5 minus 3, which is equal to +2, and r is the faraway distance, and the electric field appears radial, like it's coming from a single point charge +2. So we do not consider the separation distance for the two charges. But electric dipoles are different. If we want to find the electric field very far away, distance r, on the axis of an electric dipole, for example, we have to consider the separation distance, because even though far away it appears like a single charge, if the distance is neglected, the electric field will be zero, as dipole charges are equal and opposite, so electric fields are equal and will cancel out. But we know that the electric field of an electric dipole is not zero. This is actually how it looks like. We have to consider that little distance, and so we will find the electric field due to each charge and then sum it. The field due to the -5 charge will be bigger since it is slightly closer to the point we are considering, and it will be to the left in this direction because opposite charges attract, while the field due to the +5 charge will be smaller and in the opposite direction. So E is equal to Kq over r square minus Kq over r plus d all square. We can't neglect d here because our field will be 0, which is false. So let's find the LCM, which is r square bracket r plus d all square. R square divided by r square leaves r plus d all square minus r plus d all square divide r plus d all square leaves r square. So minus r square all brackets Kq is equal to E. R plus d all square is equal to r square plus d square plus 2dr minus r square over r square all brackets r plus d square all brackets Kq. R square minus r square is 0. So 2dr plus d square over r square r plus d all square is equal to E all brackets Kq. So now we can neglect the d because we won't get 0. If we had neglected d from the beginning, we would have missed this very big term, 2dr. R is a very large number, so neglecting it would have thrown us completely off the answer. So let's continue. E is equal to Kq bracket 2dr over r square r square. E is equal to Kq bracket 2dr over r raised to the power of 4. R cancels r raised to the power of 4, which leaves r cubed. E is equal to Kq bracket 2d over r cubed, which is equal to 2kqd over r cubed. E net is equal to 2kqd over r cubed. So unlike other charges which just depend on the charge, the strength of the electric field of the electric dipole depends on the product of the charge and the distance. This quantity is called the electric dipole moment. It is represented by the symbol P, and by convention in physics, it points from the negative charge to the positive charge. In chemistry, it is in the opposite direction. So we can write this equation as E net is equal to 2kp over r cubed. This electric field also varies inversely as the cube of the distance r. This is very important and pretty interesting because we've been seeing inverse square laws since, and this dipole, just two equal opposite charges close to each other, happens to break the rule. The implication of this is that as we go farther away, the electric field from the dipole reduces faster than that of the radial field. Next, let's consider three different positions of an electric dipole placed in an external electric field, and let's examine what happens. If it is flat like this, force due to the field is equal to minus q, and it will act on the negative charge in this direction, and force equal to eq will also act on the positive charge but in the opposite direction. The charges will be compressed. If you switch it, the charges will expand. What about if the electric dipole is perpendicular to the electric field? The negative charge will experience a force opposite the direction of the electric field, and the positive charge a force in the direction of the electric field. So imagine it's like a tap. Something is pushing here and also pushing here. It's going to turn, it's going to rotate. So if you've done rotational dynamics, you'll know that this turning effect produced by force is called torque, and it is equal to the force times the perpendicular distance between the force and the axis of rotation of the force. In this case, torque on the negative charge would be force times d over 2, and the positive charge would experience a torque equal to force times d over 2. So the net torque is equal to Fd over 2 plus Fd over 2, which is equal to Fd. It would add since they are turning in the same direction. Our third position is when it is at an angle theta to the electric field. Let's find our torque, which is the force times the perpendicular distance. There are many ways to approach this. We can find the perpendicular force or the perpendicular distance from the axis of rotation of the force. Let's do the perpendicular distance. These angles are corresponding angles, so they are equal, and here is d over 2. The perpendicular distance, that's the opposite from trigonometry, would be d over 2 sine theta. So the torque on negative charge is equal to Fd over 2 sine theta. Net torque from both charges is equal to Fd sine theta. F is equal to electric field times charge, so the torque is equal to EQD sine theta. Can you remember what this quantity is? I bet you can. It is the electric dipole moment, so we can write this equation as F is equal to EP sine theta. We can use this equation also for the perpendicular position or any position at all, just that we know for the perpendicular theta is going to be equal to 90, so sine 90 is 1, so F is equal to EP, which is the same thing as what we got, FD. FD will give EQD, which is equal to EP. So T is equal to EP sine theta is the general formula you can use to find the torque of an electric dipole. If this video has been helpful, consider liking it and subscribing. Thank you so much. Work done of an electric dipole. So we know linear work done is equal to the force times distance. This rotational work is basically the same thing. It is torque, which is like rotational force, times the angular distance or angle of rotation of the dipole. So integrate. W is equal to the integral of t d theta. We know t is equal to Pe sine theta. So W is equal to the integral of Pe sine theta d theta. P and E are constants, so we can bring them out. W is equal to Pe integral of sine theta d theta. Let's say we are rotating the dipole from initial angle theta 1 to final theta 2. Integral of sine theta is minus cos theta. Pe minus cos theta theta 2 theta 1, which is equal to minus Pe cos theta 2 minus Pe cos theta 1, which is equal to minus Pe cos theta 2 plus Pe cos theta 1, which is equal to Pe cos theta 1 minus Pe cos theta 2. You can bring Pe out. W is equal to Pe bracket cos theta 1 minus cos theta 2. And that's our formula to find the work done. How do we find the potential energy? Work done is equal to the change in potential energy. UF, final potential, minus UI, initial potential energy. Let's use our work equation to find the formula for the potential energy. We can't use this one since we've already simplified it and it's now initial minus final. So let's use this. We'll see that UF is equal to minus Pe cos theta 2. So generally, potential energy is equal to minus Pe cos theta. Let's take note of something. Things usually go from a higher potential energy to a lower potential energy, just like water in osmosis. So the final potential UF is smaller than UI. The electric field always tries to get the electric dipole to a lower potential energy. From our potential energy equation, we know that the lower potential energy is when the dipole moment points in the same direction as the electric field. So the electric field always tries to align the dipole moment vector with the electric field. Let me show you how. For the dipole -5 and +5, the dipole moment points this way. So it will rotate like this to align itself with the electric field from 90 degrees to 0 degrees. Ui is equal to minus Pe cos theta. Theta, which is the angle between the dipole moment vector and the electric field, is equal to 90. That means Ui is equal to minus Pe cos 90, which is equal to 0. And Uf is equal to minus Pe cos theta. Theta is equal to 0. So minus Pe cos 0 is equal to minus 1. This has a lower potential energy than the initial value. It will be the same if we switch the charges. It will rotate this way to align the dipole moment vector and the field in the same direction, and that's also the lower potential. Uf is equal to minus Pe cos theta. Theta is 0, which is equal to minus Pe cos 0, which is equal to minus 1, and Ui is equal to minus Pe cos theta minus Pe cos 90, which is equal to 0. So Uf has the lower potential. Let's review the formulas we've learned. Electric field on the axis of an electric dipole is equal to 2kqd over r cubed or 2kp over r cubed. Electric dipole moment is equal to the charge times the separation distance, qd. The net torque is equal to eqd sin theta or fd sin theta or pe sin theta. Work done on dipole in a field is equal to Pe brackets cos theta 1 minus cos theta 2. Potential energy is equal to minus Pe cos theta. An electric dipole of charge 200 coulomb each and separation distance 2 times 10 raised power 7 aligned at 30 degrees with the direction of a uniform electric field of magnitude 5 times 10 raised power 4 Newton per coulomb. Calculate 1. The electric dipole moment. 2. The torque. 3. Potential energy at 30 degrees. 4. Work done in aligning with the electric field. Let's calculate the electric dipole moment. P is equal to QD. Q is equal to 200 coulomb. D is 2 times 10 raised power 7. So P is equal to 200 times 2 times 10 raised power 7, which is equal to 4 times 10 raised power 8 coulomb meter. The torque is equal to Pe sin theta. P is equal to 4 times 10 raised power 8 coulomb meter. E is equal to 5 times 10 raised power 4 Newton per coulomb. And theta is equal to 30 degrees. So torque is equal to 4 times 10 raised power 8 times 5 times 10 raised power 4 times sin theta, which is equal to 4 times 10 raised power 8 times 5 times 10 raised power 4 times half, because sin theta is half. 2 cancels 4, which is 2. So this is equal to 2 times 5 times 10 raised power 8 times 10 raised power 4, which is equal to 10 times 10 raised power 12, which is equal to 10 raised power 13. The unit is coulomb meter times Newton over coulomb, which is Newton meter. So the torque is equal to 10 raised power 13 Newton meter. Potential energy at 30 degrees. Potential energy is equal to minus Pe cos theta. So it is equal to minus 4 times 10 raised power 8, that's P, times 5 times 10 raised power 4 E times cos 30. So potential energy is equal to 1.732 times 10 raised power 13. Then 4. Work done in aligning with the electric field. Work done is equal to Pe brackets cos theta 1 minus cos theta 2. Theta 1 initial angle is equal to 30 degrees. Theta 2 final angle is equal to 0 degrees. So it's going to be P 4 times 10 raised power 8 times E, which is 5 times 10 raised power 4 brackets cos 30 minus cos 0. Cos 0 is 1, so it's going to be 4 times 10 raised power 8 times 5 times 10 raised power 4 brackets cos 30 minus 1. If you put this in calculator, you get minus 2.68 times 10 raised power 12 joules. Another question. A molecule of a substance has a permanent dipole moment of magnitude 10 times 10 raised power minus 30 coulomb meter. A mole of this substance is polarized by applying a strong electric field of magnitude 10 raised power 7 volts per meter. The direction of the field is changed by 60 degrees. Find the heat released by the dipole in aligning its dipole along the new direction of the field. So P is equal to 10 raised to the power minus 30 coulomb-meter. But this is just for one molecule. The question asks for a mole. So we know that 1 mole contains 6.02 times 10 raised to the power 23 molecules. So 10 raised to the power minus 30 will contain 6.02 times 10 raised to the power 23 times 10 raised to the power minus 30, which is equal to 6.02 times 10 raised to the power minus 7. So P of the mole is equal to 6.02 times 10 raised to the power minus 7. Theta 1 is equal to 60 degrees, while theta 2 is equal to 0 degrees, because it is stable at first, it's polarized, that's made to go in one direction along the electric field. Then the angle of the electric field is changed by 60 degrees to here. So now it's at 60 degrees to the field, and the tendency will be for the electric dipole to realign to 0 degrees, which is what it does. And they are asking us the work done when it realigns with the new electric field direction. So theta 2 is equal to 0 degrees. Work done is equal to PE bracket cos theta 1 minus cos theta 2. P is equal to 6.02 times 10 raised to the power minus 7. E is equal to 10 raised to the power 7. Work done is equal to 6.02 times 10 raised to the power minus 7 times 10 raised to the power 7 brackets cos 60 minus cos 0. 6.02 times 10 raised to the power minus 7 times 10 raised to the power 7 is equal to 6.02. So work done is equal to 6.02 brackets cos 60, which is half, minus cos 0, which is 1. Half minus 1 is minus half. So work done is equal to 6.02 times minus half, which is equal to minus 3.02 joules. That's all. Thank you so much for watching. Always keep learning and always leave a question to be answered in your heart.